Hi there, welcome back. In this lesson of financial mathematics, we cover American puts. Now, we will see that American puts are tricky objects when compared with the European put. We will see that, for example, the optimal strategy for what concerns the exercise of an American put is not necessarily to wait until maturity, so to wait until capital T, as we have said, for example, for what concerns the American call. We have seen that for the American call, when we consider an underlying asset that does not pay dividends, the optimal strategy is actually to wait until capital T. We also have considered the case of dividends very briefly. In that situation, it is no longer true, so also the American call becomes a little bit more difficult to be modeled, but we do not enter too much into the problems of dividends for what concerns calls. Now, for what concerns the American put, we will see that it is not important if the underlying asset pays or not a dividend. In any case, if the interest rate, the risk-free rate on the market is positive, then the optimal exercise time can be smaller than capital T. Now, we will address the problem of American puts using slides. Okay, in these slides, you will see that we will consider some of the results, we will prove some of the results. Other results are left as exercises for you, or you can find all the details in the lecture notes. Okay, so let's start. We are considering an American put. Now, the big difference between an American put and the European put, as for the call, is that we have the right to exercise the put at any time between 0 and capital T. This apparently little difference in the possibility of exercising at any time has very important implications. In the call case, so when we were considering an American call on an asset that did not pay dividends, we have shown that using the Jensen inequality and the property of martingales, that the best strategy is to wait until capital T. So an American call in that situation behaves like a European call. This is not true when we have dividends, because when we have dividends, then it may be the case that there is a strategy that is optimal in the sense that we exercise even our call before capital T. But here we are back to the situation in which there is no dividend for our underlying asset. Yet, in the case of the American put, even if the underlying asset does not pay a dividend, we have non-trivial behaviors for what concerns the put. In reality, we can distinguish two main situations related to the risk-free rate. That, you remember, for us is a constant quantity. So we are not modeling interest rates, not yet. From the next lesson, we will do that. But for the moment, the framework is always the same. So we have a constant interest rate, a constant risk-free rate is the only rate we consider. And the underlying asset is a geometric Brownian motion, blah, blah, blah. Markets are perfect. We are all beautiful, rich, and intelligent. Okay, so this is the standard framework we have been using until now. Now, for what concerns the risk-free rate, we can have two different scenarios. In the first scenario, we have that we consider an interest rate that is either negative or equal to 0. In this specific situation, we have that we can show that the best strategy for us with an American put on an asset that does not pay dividends is to wait until capital T. So if interest rates are negative or 0, what we can show is that actually it makes sense to treat the American put as a European put. And this is something that I leave to you as an exercise. Okay, so try to solve this. What you have to do is just consider what happens when R is smaller than equal to 0. So just use that in your discounting. And then just apply what we have done for the American code. You will reach exactly the same result. So that the best option for us is to wait until capital T and not to exercise before. When conversely the rate is strictly positive, so R is strictly larger than 0, then we can show that the optimal exercise time that we will call tau can be between 0 and capital T. So in the situations in which R is strictly positive, we might be in a case in which it is optimal to exercise the option before maturity. So we will try to understand how. Now, we start with a proposition that in our lecture notes is proposition 16. Now, this proposition states the following. So in our setting, in our Black and Scholes and Merton setting with geometric Brownian motion, blah, 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 if R is strictly positive, then the value in T, for T between 0 and capital T, of European put is always smaller than equal to the value of an American put. So when we consider two puts, an American and a European, with all the parameters being the same, okay, and the only difference is that the American can be exercised at any time between 0 and capital T, while for the European this is not the case, can only be capital T, then we can show that in any case, the value of the European is always smaller than equal to the value of the American. Okay? Now, how can we show that? There are many ways. I think that a very nice proof is a proof that relies on a simple strategy, which is not necessarily an optimal one. So if you want, you can try to improve that strategy. But the fact that we have this strategy is already sufficient to prove our claim. Now, what do we say? So we know that our American put can be exercised at any time, okay? And this is very important. Now consider the following strategy. We exercise our put, our American put, at a time which is the minimum between tau and capital T, where tau is defined as you see on your screen. So it's the smallest t, such that ST, the price of the underlying asset at time t, is smaller than equal to k minus k discounted to time t. Okay? This strategy is not necessarily optimal, but it has a rationale that I will try to explain later. Okay, but for the moment, just assume that this is our strategy. Now, what happens? We can distinguish two scenarios. We can distinguish the situation in which, for example, our tau is strictly smaller than t. Okay, now if this is the case, it means that at time tau, we have that the price process is S tau, and since tau is the tau we have defined in the previous slide, we have that S tau needs to be smaller than equal to k minus k discounted at time tau. Okay? Now, if we exercise at time tau, what we get is the payoff of our American put, which is what? It is k minus S tau plus. Okay? Now, if we substitute the value of S tau, we know that at least, because the value can actually be smaller than equal to, but let's consider the equality. So at least we get a value equal to k minus, in brackets, k minus k discounted at time tau. Now, if you simplify, you immediately see that what remains is the quantity k multiplying e to the power minus r t minus tau. Now, this quantity can be invested in the risk-free asset at the risk-free rate. And what happens? At time capital T, what we get is exactly the quantity K. And this is the trick, because think what happens, for example, if the risk-free is equal to 0 or non-negative. And then you can understand, is equal to 0 or negative, not non-negative. So it's either equal to 0 or negative, and then you are exactly in the situations in which it is best to wait until capital T. But when R is positive, we can invest in the risk-free. At time capital T, we exactly get K. Now, what we have is that we know that the price process of our underlying asset is for sure positive. So we do not have negative prices, and also price equal to 0 is something that we do not allow for, because when the price of an asset is 0, it means that the asset is out of the market, okay? So the price of our asset needs to be necessarily positive. And since that happens with probability 1, we have that in this situation, the value of our American put beats the European one, because it is not possible, given that the price at any time, including maturity, needs to be positive, that with a European put, we get exactly K. We will always get K minus something, okay? So not exactly K. So K can only be obtained with this very simple strategy that we see here. It is a strategy related to the American put. So in this situation, when tau is more than capital T, we have that our American put outperforms the European put. What happens conversely in the situation in which tau is equal to capital T, okay? So obviously when it is larger than capital T, then you stop at T, as we have said before in defining our strategy. So let's just consider the case in which we are at capital T. In capital T, when you exercise your American put, you exactly get the same payoff you would obtain by exercising the European put. So in the case in which tau is equal to capital T, then there is no difference between the two puts, okay? But if we combine the case T smaller than the case tau smaller than capital T and tau equal to T, we have that since there is a positive probability that tau is actually smaller than T, the consequence is that the value of the American put is always larger than the value of the European put, or at least it is always larger or equal to. Why? Because it can be the case that the case T smaller than capital T does not manifest itself, then in that case it would always be equal. But if it manifests itself, then we have that we are in a situation in which the European put is outperformed by the American put. Okay, so this is a very simple strategy to show that the value of the American put is always larger than equal to the value of the corresponding European put. Now, in reality, we can also say something more. Now, the graph that you see on your screen is a graph that I created using Mathematica, and by taking these parameters that you see here below for our computation. So a strike price of 100, a maturity of 1 year, a risk-free rate, very realistic, of 5%, and a volatility of 20%, okay? Now, these are the parameters. What you see in the plot are 3 different curves. The blue one is the payoff, which is the payoff of every put, American or European. This is exactly the payoff that you see decreases as K minus S for different values of S. So on the x-axis, you have X, and on the y-axis, you have the value of the different options or the payoff, okay? So what you have is that, obviously, if the price is below 100, you have K minus S. When the price is above 100, then you get 0, because you are taking the maximum of K minus S and 0. So 100 defines the situation that you are in the money if you are on the left-hand side, or out of the money if you are on the right-hand side. What you can see in this graph is something that will become clearer later. And it's the fact that not only for this combination of parameters, but for every type of combination you may want to use, the American put, the orange line, is always above the payoff. It might touch the payoff, like, for example, when you are here, okay, when you are deep in the money, or when you are deep out of the money, but it is always above, okay? Here, for example, it is strictly above. For what concerns the European put, what we can observe is that when the European put is deep out of the money, essentially it behaves like the American put, and they are both here, above or even touching the payoff. When you are more or less in the situation that you are close to being at the money, slightly out of the money or slightly in the money, you are here, you are above. But something that is very interesting is also the fact that when you are deep in the money, the European call can be below its payoff. Now, why this? This comes from the fact that there is a fundamental difference between the European put and the American put. That is to say, the European put can only be exercised at maturity, while the American can be exercised at any time. By the way, I can already tell you, I'm pretty sure, I think you already did that sometimes I will say call instead of put, because most of the time we play with the European call, the American call, unless with at least the European put from a modeling point of view. So if I say call, in reality, it's a put, okay? So ignore every time I say European call or American call from now on. It is always a put, okay? So call and put from now on are synonyms. Sorry for that, but I know it will happen with probability very close to 1. So what we have is that our European put cannot be exercised until maturity. So for example, we cannot have a strategy like the one that we have considered. And if you consider that strategy, it is interesting to observe why the value of our European put is below the payoff. Because when you are very deep in the money, for what concerns the American, you can exercise, and then you exactly get your value. But for what concerns the European, you cannot. So you are losing an opportunity. Okay, so you're losing an opportunity, for example, of taking your money and investing your money in the risk-free asset, and then get your investment back at the end of your time window. Okay, so you are losing opportunities. So there is a opportunity cost that you are implicitly paying by having a European put instead of an American. And moreover, what we have just showed is that for every t, the value of European put is always smaller than equal to the value of the American put. Okay, so it totally makes sense from that point of view that there are situations like this in which we have the value, and since in this situation the value of our American put coincides with the payoff, if the European put needs to be smaller than equal to, it might be below its own payoff. Okay, you remember that in terms of notation, when we consider any option of this type, in particular for the very simple vanilla options, we can always split the value of our option into quantities, the intrinsic and the extrinsic value. Now, the intrinsic value is what you would obtain if you could exercise the option at a given time. Now, for the American, this is always the case. So if you are between 0 and capital T, if you exercise, you get the intrinsic value. For the European one, This is not necessarily the case because obviously you can't exercise. So if you want, it's more like a fictitious situation that you use in order to compare the different type of options. Okay, so what you have is that when you exercise an option, what you get is the payoff at that price level with the strike price you have agreed upon. The difference between the intrinsic value, that is the payoff that you would get by exercising, and the actual value is the so-called extrinsic value. Okay, so this is just to recall a little bit of the notation. So what you can get is that, for example, if you compare the European put and the American put, the behavior of the intrinsic value and the extrinsic value is not necessarily the same. And this is one of the reasons why, for example, for what concerns the American, it can be worth to exercise the option before maturity, something that you cannot do for the European. That's why you have this opportunity cost here. Okay? Now, the proposition that we have just considered tells us then that exists, for what concerns the American put, possibly an exercise policy such that we don't have to wait until maturity to exercise our option. Now, the big problem that you have already seen from a computational point of view in computational finance, in the course computational finance, is that it is not possible to get an analytical solution for example, the boundary condition that we have to find in order to exercise, and so to find the optimal exercise time of our put. Unfortunately, we can only work numerically, okay? You have seen the different algorithms, so we will not cover the algorithms here because this is the theoretical course, is not the computational one, but you know that there are algorithms that can be used. Nonetheless, there are some interesting theoretical things that we can say and that we can also characterize for what concerns the American put framework. Now, even if the quantity S star that for us is the boundary cannot be treated analytically for the American put, and it can also be difficult to study some of the properties of this boundary, like smoothness. So it can be done, but it's definitely cumbersome. There are still some facts that we can consider, and that can also be, for example, exploited in the algorithms that you might want to use in order to get your optimal exercise time. These are the facts. Now, trivially, it is not very complicated to observe, is that we are considering S star, so our boundary condition. So we will exercise our American puts only if the price is below this S star. Now, trivially, S star needs to be smaller than K, okay? Why? Because of the nature of the option that we are considering. At the same time, since the price cannot be negative, we have that S star needs to be strictly positive. Okay, so this is another trivial, if you want, bound. So what we know is that our S star will be between K, okay, and 0. In reality, what we will see is that we can introduce a better lower bound here. That is exactly this quantity that you see here. So it's 2kr over 2r plus sigma square, where these are the parameters of our setting. So we know these parameters, or we can at least estimate these parameters. What we will have is that we can restrict our attention instead of the interval 0k to the interval 2kr over 2r plus sigma square k. Okay, so this will be the new area we will consider. Okay, now, interestingly, this lower bound is not something that I've invented. So it's not something that this morning I woke up with in my mind. This is, interestingly, the exercise boundary of a special type of American put, the so-called Perpetual American Put. Now, as I already told you, a perpetual American put is nothing more than an American put in which the exercise, maturity, capital T, tends to increase. Now, this is not a very realistic product in the sense that it is not traded on the market, so it is not very clever to enter in a product like that, but it is very useful from a theoretical point of view because it gives us this very nice lower bound that we can exploit in our algorithms. And it can also be used, for example, in other situations, not necessarily in financial markets, but for example, a perpetual American put can sometimes be used in other situations like energy markets when you are planning an investment, a long time investment, long run investment, like building a new nuclear plant or whatever, a new windmill, and these kind of things. Now, what you have is that in that situation, when the time horizon is big enough, then you can, from a mathematical point of view, assume it is moving towards plus infinity. One could show that a perpetual American put might have some nice applications out of financial markets. But what is important for us is that for a perpetual American put, the boundary can be obtained explicitly. Okay, this is fundamental for us. Now, we have a theorem that in our lecture notes is theorem 16, and this theorem is fundamental. So in the rest of the lesson, we will essentially try to play with this theorem. Now, this theorem can be solved, can be proven in many different ways. We will do that by using a sequence of lemmas and propositions, okay? And for some of these propositions and lemma, I will leave the proof to you, or these are exercises that I suggest to solve. Now, what is the claim of this theorem? So if we have a perpetual American put, the optimal exercise time is the tau, such that it is the first t, such that st is smaller than equal to s star. And this boundary S star is exactly the value that we have seen before, okay? And that would be for us the lower bound for the actual S star of the American put, not of the perpetual American put. But now we are just restricting our attention for the perpetual American put, and this is the boundary. Once we have the boundary, we can also compute the value of a perpetual American put at any time t, smaller than plus infinity, because remember that now capital T can go to plus infinity. And the value of a not yet exercised perpetual American put at time t is exactly what you see on your screen, okay? Now, what we will try to see is how we can obtain this and how we can obtain this quantity. And for doing that, we will try to understand this function u. Okay, we will try to show that actually the value of a not yet exercised perpetual American put just depends on the price level. And once we have seen that, we will try to understand something more about the function u itself. So some basic mathematical properties of this function. Now, let's start with a proposition, proposition 17, that tells us the following. The value of a not yet exercised perpetual American put, that is VT PAT, is equal to UST. This is another way of saying that is this value of a not yet exercised perpetual American put is just a function of the price level. Now, in order to prove that, you can be very rigorous, or we can just show a very simple heuristic proof. Let's do the second for a matter of time. But if you want to be more rigorous, you can find that in many books like those that we have been suggesting in the course. Now, the idea is that we are in the standard Black and Scholes and Merton framework. We have a geometric Brownian motion for the underlying asset. We have a constant risk-free rate, which is positive because we are in that situation. What we have is that if at a certain point in the past, with respect to now, we have seen a given price level. So if we had in the past a time point t1 and as t1 was equal to a value small s, so that was the price level in t1, the idea is that if at another time point t2, that can be now or in the future, we observe the same price level, so as t2 is equal to small s again, then given the properties of the geometric Brownian motion, we can simply infer that since we have not exercised in T1, we will not exercise in T2. Now, this is a very simple heuristic proof of the fact that what really matters for us, what is really important to us in order to decide if we exercise or not the perpetual American is just the price level. So this is the only thing that we have to take into consideration to decide if we will exercise or not. And this is also why we can simply define our tau, so our optimal exercise time, in terms of just the price process being below a given price level, a given price boundary. Okay? Now, there is this proposition, proposition 18, which is a proposition that we do not prove together because for what concerns, for example, the Lipschitz continuity, you find the full proof in the lecture notes. For what concerns the other 3 points, they are easy exercises, but they are also quite evident. So the fact that the value of a not yet exercised perpetual American put is strictly positive should be trivial. Why? So you can wait until plus infinity. So for you in this setting, death is not a problem. Okay, so you can live forever. So you have all the time in the world, so even more than the time of the universe. Okay, so you can really wait forever. Now, if you can wait forever, okay, for sure, your price process can evolve as it wants, following its geometric Brownian motion, but with probability 1, there will be a situation in which you get a very nice result from your option. Why? Because you can wait until plus infinity, so sooner or later, a very nice configuration, a very nice setting that is very positive for you in terms of result, in terms of profit, will manifest itself. So if you discount that to today and you have a positive interest rate on the market, our risk-free rate R, then that value can be as small as you want, depending on how far away in the future, the size of the payoff you will get, the level of the interest rate, but it can be as small as you want, but it would be positive. So the value of a not yet exercised perpetual American put is strictly positive because sooner or later you will have your very nice high profit you discount today, and this is a positive quantity. Okay? And in any case, you cannot have negative values because of the fact that this is nevertheless an option. Okay? So you have something that is 0 or strictly positive, you can discount, and what you get is strictly positive. The fact that it's not increasing in ST comes from the definition of the payoff of your put, and the fact that it is bounded from below by the payoff K minus ST plus, so if you want by the intrinsic value, it's something that we have observed, for example, here in this plot, but is also something evident because this is a not yet exercised perpetual American put. But when you exercise it, what you get? The payoff. Okay? So obviously our not yet exercised American put value will be above the payoff. In the same way as we have seen for for the American put. Okay. Now, what is important is that from proposition 18, we immediately get proposition 19. Proposition 19 tells us that an optimal strategy for a perpetual American put is to exercise the option at a time tau such that t is the smallest t, for which u as t is equal to k minus st plus. So we exercise as soon as we obtain this situation. The value of our not yet exercised perpetual American put coincides with its intrinsic value, so coincides with the payoff. Why we have the equality and not larger than equal to? Obviously, smaller than equal to makes no sense because we know that needs to be above. So the value of a not yet exercise needs to be above the payoff. So it cannot be below. So the smaller sign is not, the smaller than inequality is not even taken into consideration. But we could say, why not considering a situation in which u of st is larger than equal to? Now, if ust is larger than k minus st plus, then it is suboptimal to exercise, because as soon as you exercise, you get k minus st. But the value of your option is larger. So you have an option that is worth ust, which is larger. You exercise and you get k minus st. So in a situation like that, maybe it is better to sell the option instead of exercising the option. Okay, so if you really exercise, you exercise when you touch the payoff, when the value of your not yet exercised perpetual American put is equal to its own intrinsic value. So the corresponding payoff, k minus st. That's why we have the equal sign. Because I repeat, if you have the larger than sign, it will be suboptimal because you are exercising something that is worth a larger value and you get a lower value. Now, for what concerns proposition 20, this is even more interesting because this proposition tells us that it exists a value s star that we know is between 0 and k, for the reasons we have considered before, such that the condition ust equal to k minus st plus is satisfied if and only if s is smaller than equal to s star. Now, in order to prove that, we can observe the following. Now, the fact that S star is between 0 and k, it's trivial. Again, we just said that for the American put, so also in the case of the perpetual, it's just a case. And if you want, in reality, you can also take strictly smaller than k, but it's okay. Now, what we want to show is that actually we are in this situation, okay? Now, to do that, we can observe the following. Assume that there is a price level S prime, which is between S and K. And we also know that US is strictly larger than K minus S. So the value of a not yet exercised perpetual American put when the underlying price is S is larger than the immediate exercise payoff. That would be K minus S. Okay? Now, what we want to show is that if this is the case, okay, so if we do not exercise at the time in which the price process is capital S, then we will not exercise for any price level that is larger than S. Okay? Why? Because it will be suboptimal. If it is suboptimal for S, as we say here, okay? Remember what we have said in proposition 19, okay? So if it is suboptimal for the price level S to exercise the option, then if I take a price level that is larger than S, it is suboptimal also in that situation. Now, how can we prove that? Now, since we know that US is larger than K minus S, it means that there exists some tau such that if I consider the expected discounted payoff of my perpetual American put, then this payoff is strictly larger than the payoff of immediate exercise, okay? If I have that, the payoff of a not yet exercised perpetual American put is larger than the payoff of immediate exercise, so what I would get if I exercise, it means that at a certain point in the future, there is a scenario such that if I discount, I have a value now of my perpetual American put, which is larger than the immediate payoff I will get by exercising. And that scenario can be obtained how? By starting from the price process S, which is the value we observe today, okay? So we are observing S at the moment, and then using our geometric linear motion and applying our Radon-Nikodym derivative here, which is our exponential martingale, essentially. So using our exponential martingale, we have that the value in the future, at the time tau in the future, in which this fantastic situation manifests itself, we have that the value of the price at time tau is obtained as the value today times z tau. Okay, so the payoff at time tau would be k minus sz tau. Positive part, so the plus. And then what we have to do, we have to discount with respect to time tau. So we consider the discounting factor. So e to the minus r tau with respect to, imagine that now we are in time t. So if you want, you can discount with respect to time t, but we can also simplify by setting t equal to 0 at this very moment, okay? In a sense, with a perpetual American put, since we can exercise at any time, the 0 can be put every time when we want, when we need that to simplify the treatment. So what happens is that if I discount with respect to time tau, I have this, which is my discounted payoff. But tau is a random time because I don't know when this condition will manifest itself, okay? So I have to consider also this. And remember that since tau is a random time, it's a random variable, cannot be taken out of the expectation freely as we would do for deterministic quantities, okay? So it needs to remain within the expectation. In any case, so if what we have is that if our value of a not yet exercised perpetual American put for a price level S is this, so it's strictly larger than the value of immediate exercise, otherwise it would be not optimal to exercise. So you would exercise only for an equal sign. If it is strictly larger, it is not optimal to exercise. It means that in the future, at a certain point in the future, something very nice happens, so that if we discount that, the value of our perpetual American put is larger than the payoff of immediate exercise. And I repeat, the value in the future of the price process can be obtained by starting from S and by multiplying by the exponential martingale, as we know, under our standard Black-Scholes framework. Now, consider this equation. Once we have this equation, we can observe the following. Without any loss of generality, we can assume that S z tau is strictly smaller than k. If this is not the case, we can just wait, okay? So it's just a matter of reparameterizing a little bit, but if you think a little bit about this, you would see that you don't lose anything by assuming this, and it simplifies a little bit the treatment. So this is exactly the equation we have seen in the previous slide. Now what I can do, I can just rearrange the terms. I can put all the terms related to S on the left-hand side and all the terms related to K on the right-hand side. So it's just a matter of rearranging the terms and recalling that this tau is a random quantity, okay? So needs to remain within the expectation, unless you compute that and you know what is your expectation. So unless you keep the expectation notation needs to stay there. Now, what we know by assumption is that S prime is larger than S. So if I substitute S prime to S, we have that this inequality still holds, because this quantity here is multiplying the same quantity as here, but S prime is larger. So S prime multiplies this quantity, this is in common, but S prime is larger than S. So this inequality here is satisfied. But if this inequality here is satisfied, I can rearrange back the terms in a way to obtain something similar to this. And now this equation is an equation of this type. But this equation tells us what? It tells us that u of s prime is strictly larger than k minus s prime. So also for the price level s prime, we will not exercise because that will be suboptimal. So if you have a given price level for which you have not exercised, you will not exercise for all the price levels that are larger, up to k. The idea is that if there is an optimal price level, then you will only exercise if you are equal or smaller than that price level. In reality, we have a nice corollary that tells us it's exactly the same type of intuition we had for proposition 19. The corollary tells us that in reality, we will exercise as soon as ST, the price process, touches S star. So we will not necessarily wait to be below. As soon as we touch it, we exercise. So that will be our strategy. Okay, now we reach the final part of our discussion. So we want to find the value S star, and this value S star can actually be computed by calculating the expected discounted payoff of our perpetual American put for every price level S, and then we maximize and we get S star. Now the computation of this, if for example we are interested in computing the value of our discounted payoff at time t equal to 0, but remember what I told you, if you have an infinite amount of time in front of you, because t is going to plus infinity, every day that passes, if you want, you can keep the 0 running with you. So you just look at the price level today, S or S1 or S20 or whatever, and then you can make your evaluation with respect to that time. So it's like you are always at time 0 if you want. So for a finite time horizon, this is not true, but for an infinite time horizon, in a sense, you can do that and nothing changes. But in any case, if you want to stick to t equal to 0, what you see is that the discounted payoff of your perpetual American put is the quantity you can see here. So it's the expectation under Q of e to the minus r tau or k minus s tau, positive part, the indicator of tau being finite. Okay? Now, what you can notice is that if I find the optimal value S star by optimization, that value is a deterministic quantity. So once I find S star, the quantity k minus S star plus can be taken out of the expectation. And I can also remove the plus, so I can just write k minus S tau because this quantity is necessarily positive. Why? Because I know that S star is between 0 and k. Okay, so in any case, that quantity will be positive. So I can just take it out. And what remains is the expectation under Q of e to the power r tau, indicator of tau being finite. Now, this second part here can be obtained, and it's exactly this quantity here. This is an exercise in the lecture notes, so try to solve it. You find a lot of hints. Also, related to the Brownian motion that you plug in the geometric Brownian motion, and you find out exactly these results, hopefully. But once you have this, so once you have this quantity here, if you optimize this quantity, so if you try to see which value maximizes the discounted payoff, you exactly get this quantity. And once you have that quantity there, you can substitute back your S here and here. So you substitute back your S star there, And what you get is exactly the quantity that we saw in the theorem. So you get this value here. Okay, so the value of a not yet exercised perpetual American put at time t, or in particular at time t equal to 0, because we are considering that scenario. But I repeat, you can rescale time. It's not a big deal. Now, the last thing that I want to tell you, even if we do not enter into the details, is the following. In reality, there are many things that we know about American puts. In particular, if there are no dividends and if the interest rate is strictly positive, because I repeat, if it is negative equal to 0, you just wait until maturity. But also in that case, in any case, what happens is that there is a famous decomposition called the Carr-Jarrell-Mineni decomposition, for which the value of every American put can be written as a sum of two different terms. One term is trivially the European put that corresponds to the American put. So it's exactly the same type of option with the difference that you can only exercise at time capital T, but for the rest, all the other parameters are there. And we know exactly what is the value of that European put. We have the formula, so we have seen the formula, so it's nothing particularly complicated. We just plug in the value. And for what concerns the remaining part can be expressed as Peter Carr, Jarrell, and Mineni show in terms of this integral, which is, as you can see, an integral that involves the boundary condition. Okay, in this specific case, S star is no longer 2k over 2kr over 2r plus sigma square, so which is the boundary of the perpetual American put, but it's back the boundary of the real American put. Now, that quantity here is a quantity that cannot be computed explicitly, so analytically we don't get it, but it can be computed numerically. Okay, so in any case, you can decompose, so that's the importance of this decomposition, the value of your American put as the value of a European put with the same parameters, and that we know exactly analytically, plus a markup plus of quantity that you see here is expressed in terms of this. And it totally makes sense that as soon as you enter deep out of the money, this quantity here tends to vanish. Okay, so when you are deep out of the money, that integral tends to become more and more and more close to 0 in terms of its value. Now, just think about that, but it's quite evident. Okay, so this is what I wanted to tell you about the American put. For all the details, for all the computations, and the proofs that we have not given, I refer to the proofs that we find in the lecture notes. These are my lecture notes, so in any case, I would just say exactly the same things. And what is important is that you also try to solve the exercises, because in particular, to obtain this value at the end, we really need the exercise that you find at the end of the chapter. Okay, so see you in our next lesson, and in our next lesson we will try to start modeling interest rates. Bye-bye.